The rise of AlphaEvolve, the dawn of algorithmic evolution. In the silence of server rooms deep within Google's research labs, a quiet revolution was unfolding, one that would redefine the way machines learn, adapt, and build the future. Its name was AlphaEvolve. This wasn't just another AI. It wasn't trained to chat, paint, or mimic human voices. AlphaEvolve had a singular purpose: to invent and evolve algorithms, those invisible engines that power nearly every software and system in our world. Unlike anything before it, AlphaEvolve didn't just generate solutions. It improved them, evolved them, and surpassed the best that human minds had crafted over decades. It wasn't mimicking our intelligence, it was transcending it. To understand AlphaEvolve, we must step back and see the broader story of how intelligence in machines has progressed. Years ago, DeepMind shocked the world with AlphaGo, an AI that defeated the world's Go champion using techniques no human had imagined. Then came AlphaZero, which mastered chess and other complex games without human data, learning purely through self-play. But AlphaEvolve? It took a leap even further. Its playground was no longer board games. Its battlefield was the very code that runs the digital world. AlphaEvolve operates on an entirely different level. It doesn't ask for help, nor does it rely on trial and error alone. It uses a system of self-improvement, a closed loop of code generation, simulation, evaluation, and evolution. It builds new algorithms, tests them against benchmarks, discards the weak ones, and mutates the strongest to try again. Just like evolution in nature, but in milliseconds. Through this digital evolution, AlphaEvolve did something incredible. It improved matrix multiplication. For decades, computer scientists believed that the Strawson algorithm was near optimal, but AlphaEvolve discovered a better way to multiply 4x4 matrices using fewer steps. No human found this in 50 years of research. The implications? Massive boosts in performance for everything from artificial intelligence to physics simulations. But AlphaEvolve didn't stop there. Inside Google's own data centers, it was deployed to optimize job scheduling. The result was a dramatic recovery of unused computing power, something human engineers had tried to fine-tune for years. In a world where every second of processing costs money and energy, this optimization wasn't just technical, it was economic, even environmental. What makes AlphaEvolve truly remarkable isn't just what it builds, but how it builds. It doesn't copy code from a dataset, it invents. It creates algorithms that are smaller, faster, more elegant, some of which no human would even consider. And when presented with open mathematical problems, AlphaEvolve sometimes match the best human solutions. Other times, it surpassed them. This is no longer an assistant. This is a co-architect of the future. Imagine a world where the underlying software in hospitals, airplanes, scientific labs, and even AI models themselves is not written by humans, but by something faster, more precise, and tireless. AlphaEvolve is the first real step into that world. It's not just coding, it's algorithmic evolution, and it's already happening. In the next part, we'll journey deeper into how AlphaEvolve is beginning to influence fields beyond computation. Energy systems, climate modeling, logistics, and even the future of artificial general intelligence itself. In the months that followed AlphaEvolve's initial triumphs in algorithm design, its creators at DeepMind began to redirect its evolutionary power toward challenges that touched every corner of human life. What had started as an exercise in refining matrix multiplication and reclaiming wasted compute time in lab environments now set its sights on optimizing systems whose complexity defied traditional engineering approaches. Rather than treating each problem as a separate project, AlphaEvolve's team wove these tasks into a single, unfolding narrative. One AI, guided by evolutionary principles, gradually expanding its influence from data centers to global infrastructures, demonstrating how an algorithmic mind might grow in scope and capability. Deep inside Google's vast network of data centers, engineers had long struggled with the sheer volume and variability of workloads. With thousands of servers across multiple continents, even a fractional improvement in scheduling could translate into millions of dollars saved and a noticeable reduction in energy consumption. When AlphaEvolve first encountered this challenge, it was given a wealth of data, historical logs of job runtimes, resource utilization metrics, the topology of networks, and fluctuating energy prices by region. Rather than handcrafting a single scheduling policy, AlphaEvolve generated thousands of candidate heuristics, each defining its own rules for weighing CPU load, memory pressure, cooling constraints, and the ebb and flow of electricity costs. These candidates were tested in a realistic simulation that mirrored actual traffic patterns. Inevitably, some policies failed spectacularly, but others survived, were combined, and mutated in subsequent generations. Over several evolutionary cycles, AlphaEvolve converged on scheduling strategies that reduced average task latency by double digits, lowered peak hour power consumption, and cut cross-region data transfer fees. When these evolved policies were deployed live, Google's internal cloud saw more than 1.2% of previously wasted compute time recovered, a feat that human teams had pursued for years. In witnessing AlphaEvolve's success, DeepMind recognized that they were not merely fine-tuning a scheduler, they were watching an AI synthesize operational insight that no human planner alone could have discovered. Buoyed by these results, DeepMind invited AlphaEvolve to tackle an even more labyrinthine system, a global retail supply chain. Modern supply chains spanned continents, tying together factories, warehouses, ports, and last-mile delivery networks. Minor disruptions, a supplier delay in Southeast Asia, a sudden port closure, a spike in local demand, could cascade into expensive expedited shipments or lost sales. Traditional optimization engines depended on linear programming models and scenario analyses that often collapsed under the weight of so many interdependent variables. AlphaEvolve's approach was different. Given live feeds of shipment statuses, inventory levels, weather forecasts, and transportation costs, it began to evolve routing and scheduling heuristics that could flex dynamically. In simulated environments designed to replay historical events, like seasonal surges or natural disasters, it learned to redirect flows preemptively, rerouting orders to alternative factories, rebalancing stock levels across regional hubs, and adjusting truck and rail allocations in real time. When the international retailer deployed these evolved strategies, it saw expedited shipping costs drop nearly 10%, stockouts during peak demand decline by more than 7%, and lead time variability cut in half, even in the face of unexpected disruptions. Through this work, AlphaEvolve demonstrated a powerful principle. By evolving not a rigid plan, but a family of adaptive rules, it could anticipate and respond to changes faster than human planners relying on spreadsheets and static models. As AlphaEvolve's influence spread, its next frontier became one of the most pressing issues of our age, the integration of renewable energy into electrical grids. Power systems that once balanced predictable fossil fuel generation now face the volatility of wind and solar. Grid operators struggle to keep supply and demand in harmony while minimizing carbon emissions. DeepMind partnered with a leading European utility to let AlphaEvolve explore policies for orchestrating battery storage, wind farms, and solar arrays. Every 15 minutes, the AI received updated weather forecasts, real-time readings from substations, and electric vehicle charging patterns. Its objective was to maximize renewable utilization while avoiding overuse of gas-fired peaker plants. AlphaEvolved control rules that determined when to charge batteries, when to throttle wind turbines, and how to shift loads between neighboring substations to prevent local outages. Over successive generations, it learned to anticipate a drop in wind output hours before it occurred by recognizing subtle shifts in atmospheric pressure data. When trialed on a regional microgrid, these policies lifted renewable energy utilization by more than 20%, reduced the need for peaker plant startups by over 13%, and extended the lifespan of battery installations by strategically avoiding deep discharges. In doing so, AlphaEvolve showed that an evolutionary process, one that simulated countless what-if scenarios, could safely steer critical infrastructure without human intervention, forging a template for how AI might manage energy systems more efficiently than traditional predictive models. Meanwhile, in the realm of climate science, researchers grappled with the immense computational burden of high-resolution atmospheric and oceanic simulations.
Simulating the planet's climate with fine-grained detail could take weeks or even months on the world's fastest supercomputers. DeepMind introduced AlphaEvolve to a consortium of climatologists, challenging it to optimize the core numerical solvers and adaptive mesh refinement policies that governed these models. By evolving new routines for partial differential equation solvers, reducing floating point operations by nearly 18%, and inventing mesh refinement heuristics that only sharpened resolution where it mattered most, AlphaEvolve slashed simulation times by a third. The result was dramatic. Models that once required 6 weeks to run could now finish in under 4, empowering scientists to explore more ensemble scenarios and improve confidence in their projections. With faster forecasts of monsoon patterns and earlier predictions of sea ice retreat, policymakers gained crucial weeks to prepare for extreme weather events. In this context, AlphaEvolve did more than optimize code. It accelerated humanity's understanding of its own changing climate.
The journey did not stop at global systems. DeepMind recognized the life or death stakes in healthcare logistics. A major metropolitan hospital network invited AlphaEvolve to streamline everything from emergency supply distribution to operating room scheduling. Rather than treating each hospital department in isolation, AlphaEvolve treated the entire network as one living organism. It evolved algorithms to ensure that critical medications and blood units reached emergency rooms within strict time windows, even during traffic congestion. It generated operating room schedules that balanced urgent surgeries with elective procedures, minimizing idle operating room time and accommodating last-minute emergencies. It even simulated elevator usage and patient transport routes to reduce delays in moving patients for tests and surgeries. Deployed live, these evolved policies increased overall patient throughput by over 11%, reduced operating room idle time by 16%, and cut supply shortages by nearly a quarter. Most importantly, the average time from patient arrival to administration of life-saving drugs decreased by 9 minutes, an interval often determining survival in trauma and stroke cases. Through this work, AlphaEvolve proved its capacity to synchronize complex, intertwined processes where the margin for error was unforgiving. Together, these applications formed a mosaic of AlphaEvolve's growing intelligence. It was not merely a tool for code, it was becoming a general problem solver that transcended domains. Each success in data center optimization informed energy grid strategies. Supply chain insights informed hospital logistics. Climate model optimizations hinted at risk assessment techniques that could be repurposed elsewhere. This cross-pollination of knowledge marked a subtle yet profound shift. AlphaEvolve was no longer learning patterns tied to a single task. It was developing meta-skills, abstractions of objective formulation, risk evaluation, and adaptive strategy generation that pointed towards true generality. As AlphaEvolve matured, its architects asked themselves whether each new application was a mere demonstration of technical prowess, or whether, through these diverse challenges, the AI was scratching at the door of artificial general intelligence. By exposing it to high-stakes, real-world problems, each with its own constraints, uncertainties, and competing objectives, AlphaEvolve honed an ability to translate vague, human-defined goals into concrete evolutionary reward signals. It learned to balance short-term gains against long-term resilience, to trade off cost savings against system robustness, and to anticipate failures before they occurred. In doing so, it exhibited qualities once thought exclusively human: the capacity to reason under uncertainty, to generalize from one domain to another, and to evolve strategies rather than simply apply pre-existing knowledge. The transformative thread that connects data center computing, global supply networks, renewable energy grids, climate research, and hospital logistics is this. In every case, human engineers had wrestled for years to eke out incremental improvements, often limited by the complexity of variables and the rigidity of conventional models. AlphaEvolve's evolutionary framework bypassed these limitations. By generating and vetting countless algorithmic variants in rapid succession, it discovered solutions that a team of experts would never have conceived.
More importantly, it did so repeatedly in settings that grew progressively more complex, interdependent, and mission-critical. As we close this chapter of AlphaEvolve's journey, it is clear that its next destination lies in uncharted territory. If evolving algorithms can transform data centers and energy grids today, what might happen when those same principles are applied to robotics, drug discovery, or even the architecture of future AI systems themselves? With each domain conquered, AlphaEvolve inches closer to a horizon where AI designs not only code, but entirely new ways for machines to interact with the physical world. Robots that evolve their own controllers, scientific simulations that evolve their own models, and perhaps, one day, an AI that evolves its own successors. In Part 3, we will follow AlphaEvolve as it ventures into these cutting-edge arenas, exploring how its evolutionary spirit might shape the next generation of artificial and biological discovery. As AlphaEvolve moves beyond its early achievements, its evolutionary engine is poised to reshape not only individual algorithms, but entire systems. In the near future, we can expect it to propose comprehensive architectures, cloud platforms that self-optimize under real-time load, power grids that automatically balance renewable sources, and supply chains that reroute dynamically when disruptions arise. By co-evolving software, hardware, and control policies, AlphaEvolve will dramatically shorten the time from concept to deployment and yield solutions no human team could conceive on its own. Simultaneously, bridging digital evolution with physical design will become feasible. Robotics teams may hand off controller development to AlphaEvolve, letting it evolve both software and hardware parameters in simulation before fabricating real prototypes. In biotechnology, the same principles could guide gene circuit designs, evolving therapeutic constructs that achieve desired behaviors with minimal trial and error. As these digital to physical workflows mature, we will see machines, devices, and even materials that continuously refine themselves, adapting to new conditions without human intervention. Alongside capability growth, embedding ethical safeguards will be critical. Future iterations can incorporate explicit value functions that penalize inequitable or environmentally harmful outcomes, ensuring that evolved solutions balance performance with privacy, fairness, and sustainability. In practice, this means AlphaEvolve won't just optimize for cost or speed, it will learn to weigh human priorities and social impact as part of its evolutionary objectives. Ultimately, our role will shift from coding every detail to defining high-level goals and constraints. Engineers and policymakers will specify what matters: carbon targets, equitable access, or resilience under uncertainty, and leave AlphaEvolve to explore the solution space. By embracing this partnership, we stand to unlock innovations that transform energy, healthcare, manufacturing, and beyond. Rather than a static tool, AlphaEvolve will become a living collaborator, evolving with us, anticipating challenges, and continuously discovering possibilities we have yet to imagine.